Good afternoon, everybody. It's my great pleasure to be giving a presentation at IOSENS 2021. My name is Margaret from the University of Strathclyde in Glasgow. Firstly, I would like to say thank you to the organising committee for such an interesting programme this week, and also to thank Dr. Ebru Sukurugulu for inviting me. Right. I'm going to be talking about Tribo-Corrosion Maps in Biomedical Engineering. So, firstly, the aim of the presentation is to give some information on Tribo-Corrosion Maps which have developed in the biotribology domain. Why are they useful and how could they be modified based on the nature of the tribological contact, that is, the two surfaces in contact in the corrosive environment. Okay, so if we just look at the information that a map can provide, and any kind of map can provide information on landscape, most convenient location between route between two locations, and metrics. So we're quite used to using maps in that sort of context on a day-to-day basis. And materials map is exactly similar. The analogy is, landscape would be surface morphology, the most convenient route between two locations. That's the optimized parameters, identifying safe regimes, and metrics. The kilometers for a map that we normally use, as opposed to the wastage rates for the materials map, degradation rates. Okay, so basically, if we look at the context of tribo-corrosion, we're talking about many different kinds of applications in the globally. If you think about oil and gas, so the conventional oil and gas environments, tribo-corrosion is a major issue in terms of the transport of the oil, and also in terms of the corrosion of the rigs, and indeed erosion corrosion, depending on the kind of the speed of the waves, etc. And the presence of particulates. This is an example of tidal turbines, and these are the renewable energy areas where erosion corrosion is an issue. And for wind turbines, we also have erosion corrosion of the leading edge of blades of turbines. But in the biomedical scenario, this is just for hips, hip implants, we get tribo-corrosion here at the interface of the two replacement hip implants. We also get a fretting corrosion here on the stem. So tribo-corrosion covers so many different domains. I'm just going to be specifically talking about the biotribology domain today. Okay, so my work in the area started with erosion corrosion, and many moons ago now, but this is some work we published very recently, a simulation of hail impact erosion. And if you think about the energy that a particle impacting a surface has, the particle impact results in some energy transfer to the target. Now, the energy can be consumed in terms of elastic work, plastic work, and depending on the toughness of the material, can result in brittle fracture, but also the energy can actually result in frictional heat. So many different kinds of energy transfers in terms of erosive impact. Okay, so the erosion variables, we generally have many different kinds of variables. These include things like the velocity, the particle size, shape and concentration, impact angle of the particle to the surface, because that tangential velocity, normal and tangential velocity components can be quite significantly different in terms of the erosion of the surface, and then of course the materials properties such as the strength and the toughness. The corrosion variables tend to be electrochemical potential, hydrogen ion concentration, temperature, that is the activation on the surface, and the presence of anions, chlorides, sulfides, etc. So this is the first wear map that was generated, which included a mathematical model and a sort of collation of experimental results developed by Professor Session Lim. Now he's now Professor Session Lim in the University of Singapore. He was working with Professor Michael Ashby in University of Cambridge in the UK. The main thing about the map is this is normalized pressure and velocity, is that as we change the variables, we change the erosion or the wear regimes. It's mild oxidation wear here and severe oxidation wear here. This is where oxidation is very high, because as we increase velocity, we increase, and indeed pressure, we increase frictional heat. That means very high oxidation rates. As a result of the formation of oxides on the surface, and those oxides being ductile, the wear is reduced. In this case, the oxides are removed, and at very high normalized pressures and velocities, we get melt wear. Okay, so in 1990, scientists from Hyderabad in India, Sundararajan, presented this in the University of California, University of Berkeley in California. And I was very fortunate, really, because it was just at the end of my PhD, and I sat through the presentation. I was absolutely, or at least absolutely astounded and interested, because I had started doing a little bit of this at the end of my PhD, but then I saw this fantastic mathematical model of the erosion oxidation regimes. Now here we have velocity and temperature, very simple erosion oxidation map, just showing that as we increase the velocity and increase the temperature, we get more oxidation dominated regimes. As we increase the particle concentration or flux, the metal erosion regime shifts to higher temperatures. The main thing about this map by comparison to the wear map is it's a slightly simpler presentation, because the extent of frictional heating on an erosion oxidation scenario is much less than in a sliding wear scenario, obviously, because you have the you have the integral surface sliding against the counterface. So that's the difference really in the boundaries. This is the corrosion map developed by Pourbet, the Belgian scientist, and the Atlas of Pourbet diagrams that he generated. It's really the bedrock of the aqueous corrosion literature, as electrochemical potential and hydrogen ion concentration, showing that as these change, passivation and corrosion, this is metal ion dissolution regimes change. This is the immune regime. Okay, so what we attempt to do in our work is to combine the tenets of the erosion oxidation map, the sliding wear map, and the aqueous corrosion map to develop an erosion corrosion map. So I'm going to show you some work that we did in 2004. This work was carried out by my PhD student, who is now based at Sheffield University as an academic, Dr. Buddha Hafjana. This is an example of erosion corrosion of a pipe, showing degradation at the bend, generally because the particles tend to pile up in that location, and these high particle concentrations cause high wastage. This is a polarization curve showing the active to passive region, and then the going on to transpassivation as a function of ramping up the electrochemical potential. What are the possible interactions between erosion and corrosion? Erosion can enhance corrosion, that is removal of the passive film. Corrosion can inhibit erosion through formation of ductile film, oxide film on the surface. Indeed, it can be a sulfide film. And corrosion can enhance erosion through dissolution of phases within the material, and that, as in the case of metal matrix composites. Okay, so the erosion-corrosion interaction which we identified, this is the erosion and total corrosion. These are the enhancements of the two processes, or rather the interactions between the two processes. Okay, and what we did was we just divided some very simple inequalities just to define erosion-dominated, corrosion-dominated behavior. Okay, now I like to tell this story because the development of the Erosion-Corrosion Map, I don't think it could have been possible had I not attended 2 conferences back to back in 1994. These were in Cambridge and in London. It was the Erosion Conference in Cambridge, and followed by another week in London at Imperial College. And I think about a fortnight later, I was travelling down the Kingsway in Manchester, and this is a little bit of a light bulb here, and the traffic lights went from red, from green to red, and then to green again. In that short interval, I'd worked out the boundaries of the Erosion-Corrosion Map. Now this is what, that was 1994. The following year, we generated a paper just to show what those boundaries were in the conference proceedings of the Cambridge conference proceedings published, and where problem was that we then had to develop a series of experiments to verify the boundaries, which we did in a paper we published in Material Science and Technology, and that was subsequently followed by an erosion-corrosion mapping algorithm developed by mathematical models, and these are the results here. It was my student Nigel Corlett that generated this particular diagram. This is particle velocity versus applied potential. We get the pure erosion dominated regime here, and these are the dissolution and passivation dominated regimes here. If we ramp up the velocity here, we go from dissolution dominated to erosion dominated, and passivation dominated to erosion dominated here. Now going back to my student Pooja Vijana, he did some further work when he arrived in Strathclyde in 2002, and essentially what he did was, this was the original pour bay diagram for iron, and this is the erosion-corrosion map for iron. Okay, so we had done this just concentrated in iron and iron chrome system. So immunity here corresponds to the pure erosion here. And he expanded the analysis to pure metals. We looked at 4 pure metals, including iron, nickel, copper, and aluminium. And this is the result for results for nickel. You can see here much higher immunity regime here, and a much greater pure erosion regime here. Now, shortly afterwards in Strathclyde, there were a number of Egyptian students who arrived, who were really absolutely fantastic, and did some great work on erosion corrosion modelling and mapping. This is what Tariq Abda El Badia did in his PhD, looking at metal matrix composite materials. Basically, we looked at the interactions again, these inequalities that I showed you earlier, and concentrated mainly on the interactions, delta Ke, delta K. So these are the inequalities that we used for the measurement of the different regimes, or the establishment of the regimes. This is the synergistic effect, where the del Ke is much greater than del Kc, and vice versa. This can be measured electrochemically, this can't. Okay. Now, Tariq developed these maps. This is 2 meters per second to 4 meters per second. 4 meters per second, we have higher oxygen concentration onto the surface, and we get greater dissolution on the surface by comparison to the lower velocities. And we get, for just 4 meters per second versus 2 meters per second on the cobalt chrome tungsten carbide coating, we get higher synergies at higher velocities. This is because on these kinds of composite-based coatings, we get dissolution of the matrix around the reinforcement particles, and therefore we get higher erosion rates and synergy. If we look at the dental materials, this is just an example of mild wear here on one of the front teeth. This work was done with Kaohsiung University in Taiwan. An example of the counterface, a bit like a toothbrush during the lockdown, not dissimilar to mine at the moment, where we get wear of the toothbrush as a result of the brushing action. We looked at different soft drinks and the pH and viscosities just to see if we could map them. And this is what we did. We generated these maps. All of these points correspond to the different solutions. What we found was that there are different wastage regimes, and we got different regimes of synergy and antagonism over the surface depending on the solutions. So it was an interesting exercise to show that for these kinds of soft drinks, we can have different tribo-corrosion regimes. In terms of the hip implant, this is just an example of hip implant. We started to work in this area, and just a little bit again, I show you this image just to show you this where we're getting a lot of the issues. We developed a tribo-corrosion map based on some work we did in Ringer Solution. It was with a former student of mine who's now based in University of Illinois in the United States, and he's Director of Research for Biomedical Engineering Department. What we showed here for the simulated HIP solution was that we could develop micro-abrasion maps. This is just the regime map, the wastage map, and the synergy map based on the conditions. But in this particular area, just at the 0 folds, and just heading up to more positive applied potential, we're getting a film on the surface which is providing some protection. It's rather interesting to have observed that. So what we did was we just, based on the fact that the biomedical engineering is such an important factor in quality of life, we did further work in this area. And in fact, actually, those maps that I showed earlier, there's quite a lot of still quite a lot of interest in that particular paper, even though it was just the early maps we did, but just purely because I think implants are of great interest. Now, at the same time, around the time that I got funding of this, coincidentally, my late father, who lived to the grand age of 96, at the age of 94, and this is him here on my parents' wedding day, the age of 94, slipped and broke his hip. And one of the things that happened at the time, it was that it was sort of a bit of an eye-opener what can happen to an elderly patient. He got his hip resurfacing that didn't work, and he was unable to walk then for the remainder of his life. And the inconvenience that caused him, it was certainly generated a kind of desire in myself to actually do some further work in the area. And we concentrated again on this aspect of the wear. There's two different kinds of hip implants. It's collaboration, medical devices, doctoral training centre in Strathclyde. Now, this scientist here, Alphonse Fischer, some of you may know this person. He's editor of Wear. He's been working for many years on the concept of a protein film on the surface, the adhesion of the protein film on the surface of a hip implant, and the kind of the potential for that film to provide some protection against wear and erosion. So that's basically, he's looked at the surface morphology and the chemistry of the surface in terms of establishing what that film can do in preventing wear. These are some of the papers that he's published. Now, what are the issues in optimizing the design? Firstly, if you think about a footballer, any of us who've been watching the European the cup matches, we all know that the footballers can jump to great heights, and the dexterity they show when they're hitting the target from a long distance. I have to say, watching those matches myself this week. But the wear and tear of their hips can be quite significant, and even in their early 40s, they might need a hip implant. So they need durable implants. They also need greater articulation. Particularly younger people need greater articulation just to get the replacement, the capability that they had originally. But the problem with greater articulation and larger head is the more chance of edge wear and metal dissolution. Edge wear leads to particle formation, and third bodies can remove protective surface layers, mechanically mixed layers, third bodies, and you get a sort of a abrasive oxidation process. Now, the size of the patient, the head size can be tailored depending on the patient build, because obviously, the kind of that can be a very significant issue. And the age of the patient, obviously, older patients may not be able to tolerate the anaesthetics by comparison to a younger patient. And the in situ tribal layers may provide some protection against where we need to identify the conditions where those the performance of those layers can be optimized. Okay, so this is micro-abrasion mechanism apparatus. This is the ball simulating the head of the femoral head, so to speak, and this is just the stationary surface. We can change the load and of this, and we can change the sliding speed, and we can also instrument this, and we have done for electrochemical control. Now, these are some of the publications on this topic from our group. Now, these are just work that was published in Material Science and Engineering in 2015. I think I just want to show this is for particles and no particles, but what I really want to show in these particular maps is that if we have particles in the system, we get more micro-abrasion dominated behavior. So this passivation area is reduced, and if we change the mechanism of or the wastage regime in terms of the safe and unsafe operating regime. See these the green area is the safe regime here. We can change this if we change the erosive environments and include no particles. And in the synergy maps may also change depending on the conditions. So this is in fetal calf serum. Essentially, the micro-abrasion mechanism and safe operating regime can significantly change in these kinds of conditions. And this is more complete simulation of what's happening than in the Ringer solution. So we think that this area here is something to do with the protein layer that has been advanced as providing some protection. And this protein layer on the surface may consist of a sort of an oxidized, or at least oxidized layer. This would be chromium oxide, but also it would also have some element of the serum that is part of the solution on the surface. Okay, so what do? We looked at the effective applied load for different femoral heads. Now remember, we were talking about it earlier, the head size is very important. If we get a very large head size, we get high, at least tend to get high edge wear rates. But what we found with different head diameters, starting at 25 millimeters, we get this kind of scenario. We don't get a sort of a peak. But here, for some of the other 28 millimeters, 32 millimeters, we get peaks in the micro-abrasion rate, and they're shifting as we change the conditions. Say, for example, here it's 28 millimeters that shifts to higher loads with higher diameters. So what what we've done in previous work is actually to look at the effect of applied load in a micro-abrasion scenario, and it's essentially very similar to the earlier papers of Welch and Lancaster in sliding, where we get a sort of a, if you like, a peak in the wear rate, consistent with the formation of a tribo-oxidation layer here. And this is what we're finding here in micro-abrasion. The particles are in the contact, then they get entrained in the contact, and then there's a contact at the asperities, formation of the oxide layer, and then you get a reduction here. So we continue to increase in reduction. So our results are consistent with these. The results earlier were results on sliding were in the literature. Now, if we look at the K values, what we found was the K values tended to reduce as we increase the applied load. Okay, in terms of the maps that we generated, the different regimes of wear which we had identified in an earlier paper can change depending on the diameter, the head diameter, and the applied load. That was the paper we published in 2020, last year, and also, more importantly, on the wastage rate, we're seeing a reduction in applied load at intermediate applied loads, and essentially what we're saying really here is that we get a kind of a safe regime here at intermediate head diameters and applied load, where we can optimize the wear rate. Okay, so I'd like to conclude by just summarizing that the Tribo-Corrosion Maps are applicable in many domains. I've just included just the biomedical engineering side today. Maps for particular erosion sliding where micro-abrasion have been proposed. That's something that is work that's ongoing. And in the biotribology domain, these maps have been used in bioengineering, but have particular future applications in terms of optimizing implant architecture and indeed development of sensors, because we can combine the electrochemistry with the wear testing apparatus. So I think that possibly could be a future area of interest. I'd like to just say a few things about some of the work we do on the Tribo-Corrosion network in Glasgow. From Strathclyde, we run international meetings, and we have an international meeting series on Tribo-Corrosion. We also have a journal in Tribo-Corrosion. It's the first journal of Tribo-Corrosion internationally that was set up in 2015 and published over 150 papers last year. But I would like to say that it's open for submissions. But also, the good news is just a recent Scopus data that just emerged. We're now a site score of 3.6 and Q1 in 2 categories, so very encouraging. But what it really does show is that the work is of interest, becoming of increasing interest internationally. Okay, also just to acknowledge Professor Duncan Dowson, who passed away last year from Leeds, who developed many of the areas of significant interest in biotribology, and indeed such a pioneer in many areas of tribology. And I'd just like to pay tribute to him here. This is a conference that was in Leeds in 2016. And it's Professor Danielle Dini from Imperial College. And this was our first Tribo-Corrosion meeting in 2002 in Glasgow. Anyway, these were the kind of the people who set the whole thing up. These are my colleagues. I'm behind the camera. So just to say thank you again to the conference organisers for inviting me to give this presentation, and thank you very much for your attention.